to present his talk.
Hello, I'm Neville from DEDAUB. I am a security expert working for DEDAUB. I'm actually a co-founder. My background is in program analysis and theoretical computer science. And I'm going to be presenting something about the tooling space that we currently are experiencing, but also the tools that we're developing internally at DEDAUB. So DEDAUB is mostly known as a smart contract security auditor in the space. These are some of the clients that we work with. However, DEDAUB does more than just security audits. We also have developed tooling. Some of it is free and has been around for a long time. Actually, so Contract Library is a blockchain explorer which is designed for security researchers and also developers that want to reverse engineer smart contracts that are opaque, so no source code, or debug transactions on chain. And Watchdog is a security solution which does both transaction monitoring and also deep static program analysis, which uses formal verification techniques within it as well. So our mission at DEDAUB is to solve security problems for the Web3 space. And this is a really big problem. There's been billions of dollars hacked from Web3 projects. Just over the last month, there's been all of these hacks. You know, Euler has been hacked for $200 million, for instance. And even though we do a lot of security audits and that brings in revenue for us, I believe that security audits are not, obviously, they're not perfect, right? They are on the security side. You know, we don't find all the vulnerabilities in contracts code. In fact, it is actually impossible to find all possible vulnerabilities. But on the operational side, they are also very human intensive, meaning that they are both expensive and it also takes a long time to schedule these. And the other thing is that vulnerabilities don't wait for audits. If you deploy or make changes to your protocol and there are small changes, you don't think you might need to re-audit the protocol, but then you know, the security landscape or the security structure of your protocol might change. But not only that, the underlying protocols on top of which you build might change, and also there might be new attack vectors that emerge and that were not known to the auditors back then. And so really the solution to all of this is to adopt all security practices. There's a lot of obvious stuff over here. You know, security audits is one of them, but also I believe development processes, right? So writing very simple, elegant, well-tested code. This is easier said than done. Sometimes you need to sacrifice a few features in your protocol. Good operational security, bug bounties. But also, lately, especially with our products, there's tooling as well. So there's transaction monitoring and also continuous code verification, which kind of does, you know, the job of the security auditor, but on a large scale. And actually, these two things, the development processes and the tooling, are probably the highest ROI of these. I've also been asked lately, because we've seen a recent phenomenon as well, sometimes hacked funds have been recovered. This is uncommon. Of course, there is tooling in the space for this. You know, chain analysis does excellent tools for, you know, like law enforcement to use. But why does this actually happen? It is due to bad operational security on the part of the hacker. And so they've been identified. And why is that? I mean, they might have used a centralized exchange or, you know, used public front ends without cloaking their IP address. But I believe that hackers will, you know, they will learn from these mistakes, and, you know, some future hackers will not make the same. So in the security tooling landscape, I've kind of like categorized the tooling that I've seen for Web3 protocols. And this is based on my own experience, internally, but also looking at the market and also listening to what our clients actually need. So anyway, there's transaction monitoring, and in transaction monitoring, you get alerted when there are some transactions that are executed on the chain. There's a few tools already there, Watchdog, Forta, Tenderly. An extreme version of this is front runners. And front runners actually are, they're very fast. They can operate, in a few seconds, and they're able to, detect these things before the next block arrives. Then there's man-in-the-middle approaches, where there's transactions have to go through a third party before being executed or get cancelled ex post facto. And also finally there's code analysis and tier improving. This is probably the most interesting class of tools out there, because these perform deep semantic analysis of the code base, which is technically impossible, but we're getting there. For many kinds of vulnerabilities, we can actually find these using program analysis techniques. However, we don't believe in a few things. So front runners and also man-in-the-middle approaches, we don't believe that these are actually going to solve your security problems. So for the one hand, you are assuming with a front runner that the attacker will submit their transaction to a mempool, and that then you can simulate this transaction, and before this actually gets mined, you can go in and pause the protocol, send the transaction directly to the miner via flashbots. However, in reality, this doesn't work. First of all, it's only supported on Ethereum because the time between blocks is large enough to do so. But even on Ethereum itself, like the attacker might actually not use the mempool. They could simply use flashbots. For instance, when I use Uniswap, I also go through flashbots personally for my personal transactions, not to be front run by MEV bots. The other thing is that even if all of this is not the case, since the space is decentralized, there might be yet another front runner in the space that is there to be making money. And if an attack transaction is submitted, the other front runner, which is malicious, might actually get there before the tool that you have. And actually, it is alleged that the Euler attack, the first transaction, might have been front run. Okay, now, man-in-the-middle solutions. I've looked at a couple of these tools. Here's an example of these. So the idea is that if you have a protocol that utilizes ERC20 tokens, you can wrap them in another token. And apart from implementing things like balance off and transfer, you also implement function to freeze the funds. Okay, so then if a user hacks your protocol, you can quickly freeze the user's funds. Of course, there's multiple problems with this. The protocol is no longer decentralized. The UX and the complexity issues increase, but also can the attacker simply, if these tokens have any value, they can potentially be transferred, translated into Ether or something which cannot be blocked. So this is a problem as well. So really at DEDAUB we've focused on both extremes. The proactive approach, which is code analysis and tier improving approach, and also the fully reactive approach, which is transaction monitoring. Okay, starting wrong with being reactive rather than proactive, because it's not possible to find every single bug automatically proactively. So you gotta use different approaches. All right, so in Watchdog, the reactive approach is transaction monitoring. So you can write monitoring agents using macro-infused SQL. It's a SQL language that operates directly on streaming blockchain data. Okay, I'll show you an example when I give a demo. And then there's the proactive approach, which does deep code analysis. So this uses program analysis techniques. We model all possible executions with a lot of caveats of the smart contract to find vulnerabilities. And some of these executions will be executions that were very interesting to us as security people. But then we also utilize tier improving techniques. We've written our own tier improver in order to significantly reduce the false positive rate. So I'm not coming here to show you a tool which does not work and say, for instance, that, you know, had it been used on some other protocol, it would have saved funds. Watchdog actually already has prevented a number of hacks, specifically on the proactive part, the code analysis. It has, we figured out how to use these analyses to find real vulnerabilities on real protocols. And with that came, a number of bug bounties. So for instance, from Harvest, Primitive Finance, Precursor to Furo Combo, DeFi Saver, and a few others, multi-chain. So 10 large bug bounties over the last couple of years. We've used Watchdog to find all of these vulnerabilities. Of course, there's a lot of extra work that needed to be put in to create a proof of concept and all of that, and to interpret the results. So these are not, by all means, they're not very easy tools to use. Okay, so I'm now gonna switch over and actually give you a demo. So, okay. So this is the reactive approach of Watchdog. So this does transaction monitoring. And we've taken a unique approach to implement this. So the idea is that when a transaction gets mined on the blockchain, we can actually see all the executions, all the EVM stack traces that been produced there. And we actually turn those into a relational approach. We turn those into actually database tables. However, the thing about this kind of data is that it's streaming data. So by the time you are finished, there's going to be new data that appears on the blockchain that you also need to process. So rather than a batch processing approach that you use in something like an analytics tool, a streaming approach would work slightly differently. Say, for instance, I want to find out whenever someone withdraws funds from Tornado Cash, as an example, right? And I want to build up a list of people that are withdrawing from Tornado Cash. And I want this list to always be current. So, in real time. This is how you would write such a query. And the idea is that the coding of the arguments that are passed when Tornado Cash is called actually happens in real time. So you don't actually need to contact us and tell us, can you add Tornado Cash as one of the monitoring things? You just write it as SQL queries that automatically decode all the data involved in the transaction. And as you can see, it's 5 lines of code to get a list of Tornado Cash recipients that is updated in real time. This is a real-time table. And let's say I want to build up on this. Say I want to say, all right, so we've got a list of Tornado Cash recipients. Now I want to build up and see contracts, smart contracts that have been deployed by these people, okay? I want to get these smart contracts and also build up a list of that is updated in real time as well. And potentially, I might want to get an alert whenever a new smart contract is deployed in that. But you would get a lot of alerts, so this is not an interesting thing to do. We gotta, build up on this a little more. Okay, so this is actually how to write it. Finally, Here we've built a query which takes the smart contracts that have been deployed by users of Tornado Cash, and we see whether they actually can reference our own protocol, because they've either deployed, either in the deployment code of the protocol, they've have one of the addresses hard-coded of our smart contracts, or they've used it in one of the constructor arguments. And potentially we can also see whether they've used it in one of our initialization arguments. So once you do all of this, you get the ability to create alerts and to be reactive to events like this on chain. Okay? There's a few other examples I can show you, like say for instance, you want to see whether a multi-sig owner changes. This is the query to write. Okay? And again, and since every protocol is different, you will need to have a general approach to transaction monitoring. Okay, on the proactive side, so on the vulnerability analysis, the deep vulnerability analysis, what we have is an approach which actually takes the smart contract code which is deployed on chain or which is uploaded to the system via some other integration, and starting from the bytecode, okay, we extract high-level information starting with disassembly, our own internal representation, and finally, the decompiled version contains the same structure, almost the same structure as you would get in the original source. But this is a normalized structure which we then can apply the security analysis to. And the security analysis are actually what find vulnerabilities, days and weeks in advance, because they analyze the smart contract code almost as if you have a real auditor doing that. So we've got an analysis for reentrancy, but also like many other things that are novel, like for instance, you check certain assertions in one function, but you are not doing the same thing in another function which achieves the same effect. And that's kind of like a catch-all vulnerability analysis that you get there. So moving back to my slides. Okay, so there's a few other practical considerations that happen in the transaction monitoring. Say, for instance, you are constructing things, intermediate representations of lists of addresses and things like that. In order to query them efficiently and be able to be extremely fast in your reactivity, so that you are able to, have a very, short lag, like a few seconds, and be able to react, we've constructed within the monitoring system the ability to materialize intermediate results and index them. And there's, various materialization approaches. Okay, so the interesting thing that people always ask is, well, how can you determine all possible executions of a smart contract? Well, in theory, it is an impossible task to actually do it generally. However, this is one of those hard problems that a lot of computer scientists have been working on over the years. And if you want to learn more about static program analysis and the techniques that we have invented for Watchdog and some of its components, there's some literature in the academic journals that we've developed over the years. But I'm going to give in a nutshell how these kind of techniques work. So we start off with the smart contract, which is a computer program, and we turn the smart contract into an IR. We do it via decompilation. We turn it into an intermediate representation, which is more amenable to analysis, which kind of looks like this over here. And in this representation, everything is normalized. You don't get complex expressions. Loops are very easy to reason about. And then we turn that intermediate representation into a logic-based representation. And this logic-based representation is, you can think of it as a database which is specifically designed only to do program analysis. It's a special database. It's got, it's in memory. It constructs very efficient query plans when you've got highly recursive queries that you need to be doing if you're trying to do program analysis and understanding of the program. And it needs to be extremely fast because we need to model almost all possible executions of the program. Okay, so it's almost like a database, but for very complex recursion in the queries. In fact, in our product, you would find internally, you would find like thousands and thousands of queries that reference each other in a mutually recursive way. So then, we also use tier improving, and we've actually written our own tier improver in order to improve the false positive rate of the analysis. So a static program analysis, what can actually kill such an analysis, make it not useful, is if it comes up with a lot of false positives. Because there's so many things that a program can do that you cannot reason about very precisely, you end up, in some analysis tools, flagging a lot of the lines of code for many spurious vulnerabilities that cannot happen in practice. However, with this tier improving approach, we only keep, executions and behaviors that are, proved to happen under some circumstances. Of course, there's also caveats in here, but the idea is that using these tier improving techniques, we can model things like, the program is swapping its own funds on an AMM rather than the user's funds, and this should not be triggered by an untrusted user, except in some other circumstances and things like that. We can model all of these basic properties. Another example, a program computing interest rates via oracles should check that the price isn't stale, right? And so you have to check in the smart contract code that there are these checks, and that these checks actually refer to the price and things like that. And all of this is fully automatic, right? You don't need to actually do this yourself. There's also catch-all things like, there's multiple ways a user can change important storage variables, then all of these ways should check similar properties before they proceed. Okay, so what are the results of such an approach? Specifically, here I'm referring to the proactive security code analysis. So we've discovered a vulnerability which, if it had been executed, would have led to the draining of $1 billion worth of wealth. And this was on a protocol called multi-chain. Okay, we call this discovery phantom functions. It's a novel kind of like mechanism here. So look at this code. So this is code from multi-chain. In the multi-chain, there's a smart contract where you can deposit funds in two different ways. So on the top, you deposit funds by first approving the smart contract, and then the deposit calls transfer from, and that does a safe transfer from, which pulls your funds into the smart contract. There's nothing wrong with that approach by itself. However, there's a second approach, deposit with permit, which utilizes permit. And for those who don't know how permit works, you basically sign something on MetaMask before you actually call the smart contract, and you provide that signature as part of the call. And what permit does is it checks that the signature is valid using ECDSA encryption, cryptography. Okay, so once that, if this is valid, this is not going to throw an error, and then the transfer from will proceed. Okay? Now, try to think how is permit implemented on wrapped Ether, on WETH, okay? Possibly the largest token. This is it. So, why this is it? Permit does not actually return anything. So permit as a function, it returns void. So the return data is of the function, for those who understand the EVM internals, is actually going to be empty. So this actually obeys the ABI of permit. So when you call permit, the code will be called, the function will succeed. So now if I get, and we call these kinds of functions phantom functions, okay? So these kind of functions that were not specifically implemented, but the fallback observes the same ABI, they're phantom functions. So now let me get back to the code that I was showing you. In the first function here, most people were actually using this function, right? So they were approving, they were doing an infinite approve, and then that meant that the smart contract had thousands of infinite approvals, right? And then over here, you could actually exploit this deposit with permit over here by supplying wrapped ETH as one of the tokens, and obviously that was a very popular token. So that would have led to over $1 billion worth of currency that would have been stolen. Luckily, that didn't happen, but still, not everyone revoked their approval, so there were a couple million in lost funds. So in summary, there is no silver bullet to smart contract security. However, there are a few approaches that we believe in, including code analysis, audits, bug bounties, and monitoring. To learn more about, to get some security alpha, follow us on Twitter. Thank you.
Thanks for a very great talk. So, anyone has a question?
Thanks for the presentation. I'm really curious about the watchdog you presented. It looks like a query system that could query all the information on in real time on chain using a SQL-like language. I'm curious about how do you collect all the information on chain and store it so well in this way that can be queried so easily, and how fast is the response times, and also other transactions in the memory pool also will be inserted into these database in real time?
Okay, sure. So there's 3 questions. The first question is, how do we do it? So basically, we have our own not re-implementation, we have our own forks of existing nodes, and these forks of existing nodes, they actually perform ETL into a database. So when new transactions or new blocks are mined, we take those transactions, they are executed, and then we take the EVM frame and we put everything into a database. So that's a standard ETL process. Etherscan does something like that as well internally. Second question is, what's the delay? So the delay between the block getting mined and that information actually going into the database is around a couple of seconds, 1 or 2 seconds, right? So there's that delay to account for because the ETL process is, quite a little bit complex. The third question is whether we could do the same using the mempool transactions. So transactions appear on the mempool, we could, just take the transactions from the mempool and apply the same process. That we don't do, actually. Yeah. But it's theoretically possible. Yeah.
For your static analysis tool, where you had the specialized database for...
Is the question, how do I suggest to to implement permit or?
To use permit 2.
Oh.
Yeah, that's which Uniswap just developed.
Sure. Yeah, I'm not that familiar with the differences between permit and permit 2 actually. So, yeah, sorry.
Okay, all right. So thanks again for the last great presentation. And the first half of the afternoon session is over, so please take a break for 30 minutes and come back to the ZK track. Thank you.